All right, so today we're going to go over, I wanted to go over problems 3 and 4, specifically problem 3 from your Big O notation homework. So Big O, so that specifically had to deal with this equation, 1 plus 2 plus 3 plus 4, all the way to plus n minus 1 plus n, right? In 1 second. And that is not to be confused with, if I recall, 1 plus 2 plus 3 dot equals, yeah, and that's not to be confused with this equation, which is 1 plus 2 plus 3 all the way up to infinity, which, as everybody knows, comes up to a value of negative 112. Actually, that's kind of a lie. It uses in very, very specific situations, it is equivalent to negative 112. No joke. But also totally weird math. So if you want to look that up, that is a deep dive on that math YouTube argued about like a number of years ago. But I'm not asking about the infinite series. What I'm asking about is a convergence, right? What I'm asking about is this convergence. 1 plus 2 plus 3 plus 4 plus n minus 1 all the way to n. What is that Big O notation equal to? Well, you figure, okay, n is the highest degree, so it's got to be equal to big O of n, right? Except that it's not, because this isn't the whole picture. When you're dealing summations, it's kind of annoying. Now, why am I going into this? And why is this something that because I mentioned earlier that this is something that you'd experience in calculus too. And the reason is because this equation happens all the freaking time, or this runtime occurs all the freaking time when we're doing math, when we're writing our algorithms. It occurs when basically we are doing an efficient comparison of every pair. So suppose I have, like, I need to compare, I have these items A, B, C, D, and E. And I want to compare every item to every other item. So, not if you were to do that very naively, like you would for instance, depending on how you wrote is unique, you might have 25 comparisons. And then you skip each one of these pairs where you're comparing against yourself. Make sense? Make sense to everybody so far? So that's if you're doing it naively. However, if you're doing your comparisons and you, however, if you're doing your comparisons and you decide to write it a bit efficiently, you can ignore any duplicate pairings, right? There's no need to compare D and E, right? You don't need to, if you compare D to E, you don't need to compare E to D, right? It's the same thing. So I'll just simply cross these off, and now we're left with 4, 3, 2, 1. 4 comparisons plus 3 comparisons plus 2 comparisons plus 1 comparison. If you extend this out all the way, you get something that's very, very similar to the 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 all the way up to n, right? It's technically n minus 1. Usually it's n minus 1 comparisons, 1 to all the way up to n minus 1 comparisons. But anyway, if we look at this isn't really a linear process. It's growing each time we add something to it. In fact, it's half of this square, little less than half of the square, about this amount, right? A triangle, about half a square. What this is actually, so at the end, so what it comes down to is that this equation, 1 plus 2 plus 3, all the way to n minus 1 plus n, converges to this, n times n plus 1 over 2. That is what it converges to. So, how? Well, we can prove this mathematically through a process known as induction. All right. And we can also write, and this can be rewritten as as I completely messed up my sigma there. Sum of n, or sum of n I 1 to n. All these sum of all the numbers from 1 to n, we can simply simplify that as that is equal to n times n plus 1. So proof by induction has two rules, and if you haven't done proof by induction, it's fairly useful, especially when you think about how we prove if recursive functions work. The idea here is that the first step is that we prove this equation works for a base case. It works for some lowest possible value. So let's prove that this equation works for 1, right? The sum of all these numbers from 1 to 1 is equal to n times n times n plus 1 over 2. So let's go ahead and substitute 1 for n. So since we're just doing one number over here, this becomes 1. And now let's go ahead and substitute those n's for 1. 1 times 1 plus 1 is 2. So 1 times 2 over 2. And that just simplifies down to 2. Wait, no. That simplifies down to 1. 2 divided by 2 becomes 1. Right? So, right, this becomes 1. These become 1. It becomes 1 times 2 over 2, which becomes 1. Okay, so it works for a base case. Everybody follow? So now the part 2 is the kind of interesting part, I feel, which is that we assume 1 plus 2 plus 3 ... plus n minus 1 plus n. Or rather, I should say, it assumes that rather than n, I'm going to replace it with k. Assume that all the way to k minus 1 plus k, assume this is true. Notice all I've done is replace the n's with k's, okay? So we're going to assume this works. Prove 1 plus 2 plus 3, to k plus 1 is equal to k plus 1, k plus 1 plus 1 over 2. So what I've done there is that I assume that it works we assume that the equation I'm trying to prove is true. And then what I try to do is that I prove that it works for k plus 1. So I assume that assume that it works. Prove that this works for the next value. Now, why does this work? Well, if I prove this, then I can say, well, it worked for our base case, which is 1. And if it worked for 1, we assume 1 works. We just prove 2 works. Okay, and if 2 work, then we can show that 3, then that means that 3 has to work. And if n is equal to 3 work, then n is equal to 4 has to work, and so on all the way up to infinity. So I prove the lowest possible case, and then I show that if any case if our case works, we assume that if some case works, then the next one has to work. So we have to prove that. So let's go ahead and prove it. So 1 plus 2 plus 3 ... And let's go ahead and say k minus 1 plus k plus k plus 1 is equal to, and again, all I've done is replace the n's with k plus 1's. K plus 1, k plus 1 plus 1 over 2. Okay. So all you have, so now what the trick is that we assume, so you're like, how do we solve this? How do we even get rid of this dot, dot, dot thing? And it's a bit of a trick. The trick is this. We've already stated in our assumptions that this works. We assume that this works. So if that works, then we can replace that with the other side of the equation. We can replace this with k times k plus 1 over 2. So the entire equation becomes k is equal k times k plus 1 over 2 plus k plus 1 is equal to k plus 1 over k plus 1 plus 1, doesn't really matter, over 2. So now how do we get from here to here? Well, the fun thing is that I can always do this, right? 2. I can always do that, so that now we have a common denominator. So I can say, so now that becomes k plus 1 plus 2k plus 1 over 2. And now what I can do is I can pull out we can pull out the common factor. It doesn't seem like it's a common factor because it's on the right. Yes. 2k plus where? So what I did is I multiplied this k plus 1 term by 1. So I took this k plus 1 term and multiplied it by 1, which is, or rather, I multiplied it by a overcomplicated form of 1, 2 over 2, right? To put it over a common denominator. So all I did over there was just simply join them over that denominator. So we should have the 2 over here. On the right side, we still have k plus 1 on the other side, which will eventually be 2. But anyway, right now we have our common factor, which is k plus 1. And it normally our common factors are on the left side. This time it happens to be on the right, but we can pull it out, which means that we can pull out the k plus 1 over here, and we end up with k plus 2 over 2. What I did, you see, is that I have k times k plus 1 and 2 times k plus 1. So I just simply pulled out the k plus 1s that were multiplying 2 and k. Sorry. So I get k plus 1 and k plus 2 over 2. And k plus 2 is just, if we, you can just simply rewrite that. You can rewrite k plus 2. Oh, where's my, come on, where's my, there's my pen thing. We can rewrite that k plus 2 as k plus 1 plus 1. We can just rewrite it like that. It's still k plus 2. But now it's equal to the side that we wanted to prove. And so now that we proved that that if it works for k, that k means that it works for k plus 1, that means since it worked for 1, it's got to work for 2. And if it worked for 2, it's got to work for 3. If it worked for 3, it's got to work for 4, all the way up to infinity, whatever it needs to be. So this equation is, it holds. Now, why did I bother going over this nonsense in the class where that's not going to matter, where I'm not going to test you on this kind of thing? Well, just to let you know, this is a really common problem. You'll even probably do it in class or in homework when you do go over your infinite convergences. And I guarantee you that if you come across problem 3 as a homework or an in-class exercise, you're also going to come across problem 4 as a homework or in-class exercise or as an exam question. Most likely the latter. Problem 4 being, of course, in case you don't have that up in front of you, that's 1 squared plus 2 squared plus 3 squared dot 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 is equal to n times, sorry, all the way up to n minus 1 squared. It's 1 squared plus n squared. And that's, I always forget how this one works. I think it's something along the lines of n times n plus 1 times n plus 2. But I always remember that it's all over 6. These values might be wrong. They're probably not, but they might be. The plus 1s and plus 2s. It doesn't really matter for, they'll give it to you, and they'll just simply say, prove the left is equal to the right by induction. But it's the same process. You show that it works for 1, and then you show that it works for 2. So if it's 1, then it should be what? It would be 1, so that becomes 2 times 3. Yeah, so that's probably works. And then what you do is that if you show that it works this, you assume that's true for k plus k, and then show that's true for k plus 1. You'll have lots of practice on it, but incidentally, so for problems 2 and for problems 3 and 4, that means that for problem 3, you want to use this equation. And since you've got an n times n, that means that problem 3's answer is O of n squared, right? And that means for problem 4, that's got 3 n's that get multiplied each other. And there's a lot of nasty, and there's a bunch of distribution that you'd have to do and stuff like that, but that's boring. We can just, with big O notation, we can say, 3 n's multiplied by together. That's O of n cubed. Yes. 6, my bad. Yeah, I've got terrible handwriting. I'm sorry. You know, now you know why I do most of my work typing. So those kind of values, so also to be clear, just because I'm not necessarily in the lecture, big O, mathematicians sometimes get angry at computer scientists because we just simply refer to everything as big O. And they have distinctive terms that we'll learn in algorithms that you don't need to know about, but they've got big omega, they've got big theta, and then they've got big O. Okay, and we really just consider about big O a lot of the times. Big O means it's never going to be worse than this. So that means this equation is bounded by n over n cubed. It's never going to be better than the n cubed curve. Okay. Big omega is our lower bounds. It means it's never going to be better than this. So basically it's never, so sometimes algorithms, they have a best case scenario and a worst case scenario. You can think of big O as our worst case and big theta as our best case. Sorry, big omega as our best case. Big theta is about as accurate as it can get for some algorithms, which is basically it's never going to be better or worse than. Some algorithms like quicksort, they can't be bounded by big theta because they have such distinct best case and worst case scenarios and average case scenarios. Yes, Anamish, I see that you have your hand up.
So I watched a YouTube video that said you can use any of those notations for worst case. It's not necessarily meant that big O is worst case. Is that wrong? Because I've heard conflicting.
I'll have to look that up, to be honest. Big O, though, the point about big O is that it only puts on an upper bound. And big theta puts on an upper and a lower bound. But big omega, that puts on a lower bound. So it can always be, like, I can write a terrible I can write so big omega is a bit more, is really much more tied to best case. I'd have to double check that.
Okay, thank you. Because
feel free to send me the video and I'll take a look at it.
Yep, perfect.
Because there's always the possibility that I'm wrong, but I don't think I am. Regardless, the point being is that a lot of times you're not really going to use big omega a lot. A lot of times as computer scientists, we're just going to use big O, and a lot of times we'll use big O when we mean big theta, and mathematicians will get annoyed, but other computer scientists will know exactly what you're talking about. So, in this class, all you have to worry about is big O notation, because what we care about is worst case scenarios. Okay. All right. Before I move on, does anybody else have any questions about this homework, such as the BOGO sort portion of it, or the Hamiltonian path portion? or Rudrata path. Same deal. Yes. Number 18 is okay. So first off, so go ahead and what did you get for a Hamiltonian path? What is a Hamiltonian path? Right. So the idea here is that basically, if we've connected these things via some path, a Hamiltonian path or a Rudrata path, depending on who you ask, is some path through this map, so to speak, or this graph that basically says, let's visit each of these dots once and only once. Okay. So, and the idea here is that I gave you a very specific puzzle, but then I said I want to generalize it to some value n. Okay. So here, right, a Hamiltonian path or a Rudrata path might be 1. Let's see if I've got one. Yeah, I've got one. I've got a path, and then if I've got a path, and then if I connect to the end like this, that would make it a cycle, basically where I start and end at the same point. But I've got one. Now what I say is assume that there is a path between these stars. Okay, assume that a Rudrata path exists. Right? Assume that one exists. And I say, given this number of stars, how many total paths would you have to check? And the answer is let's go ahead and assume that given any arbitrary star, there's a path from one star to another. So we choose our starting point, right? And then we would have n-1 locations to go for our next point. So we could go here, we could go here, we could go here. I mean, in this case, we have 3, but we could easily have 4 or 5, right? Is what I'm saying. I'm saying that come up with something where the assumptions exist. I don't want to say that it's like fully connected, like a clique that you can get from anywhere to anywhere else, because that would just say you only have to check one path, right? Because you could just travel to from anywhere to anywhere. But what I'm saying is that assume that it exists and that it's, that there's lots of edges. So we have about n-1 choices for our first one, about we have about n choices, we can start anywhere. And then from there, we have about n-1 choices for our first one, about n-2 choices for our second one, and about n-3 choices for our third one, and so on and so forth, right? So what does that what does that come down to? What does that converge to as we keep multiplying in descending order? So this is as we go down from n to n-1 to n-2 to n-3 to n-4 to n-5 to n-6 to n-7, all multiplied together. Yes. It comes down to n factorial. So this is a n factorial operation. And that is if we need to, right? So we've got there's a lot of n factorial operations. Hamiltonian path, right? Hamiltonian path. Let's see, there was a Hamiltonian path problem, I think. Yep, determining whether or not a Hamiltonian path or Hamiltonian cycle exists on a graph is NP complete, as they say, which means that has a lot of fancy math behind it. Basically means it's a very hard problem. Specifically, it's the kind of problem that is easy to check the answer, but very hard to solve. By which I said, if you were to tell me that, if I zoom back here to our original, to my outline, or I guess not, but if I reconnect this stuff, right, and I was able to say, okay, I had to go here, right? This path was fairly easy for me to solve because it had a low number, but as it gets bigger and bigger and bigger, it would be harder and harder to solve, right? But but for here, it's very easy for you to see the red line gives you an answer, right? The answer is easy to check. the problem itself is harder to solve, is much harder to solve. Make sense? That's what NP complete is. Well, that's the first part of what makes an NP complete. What also makes it NP complete is that you can turn any NP complete problem into another NP complete problem, but that's a question for algorithms. And if you have questions about that, I'm happy to meet during office hours. It's outside the scope of this class. But NP complete problems are generally around, they require what's called factorial time to solve or exponential time to solve. Both very bad run times. Very, very bad. All right, other questions on this one? And again, if your answer is incorrect when you demo this, I will just simply tell you, hey, your answer is incorrect. This is why it's incorrect. Let's go and fix it. Okay. All right. So with that, I think I am ready to come around and help people.